Good afternoon. I'm Hugh Dyer, an Associate Director in RSK's Geosciences business. Welcome to the April edition of our 2024 series of Down to Earth webinars. These will cover a broad range of subjects through the year and are available afterwards on our YouTube channel alongside previous talks. Our talk today will be the second in our series of geophysics talks. Today's talk is given by Dr. Charlotte Usher from our geophysics team, providing guidance on choosing the right or correct geophysics techniques for your site. But first, a brief note on housekeeping during the talk. So all attendees' microphones are automatically muted through the webinar. During the presentation, you can post questions. Please do post questions online, and there will be a Q&A session at the end of the presentation. We'll get through as many questions as we can after the presentation. Those that can't be answered due to time constraints will be answered after the webinar. Shortly after the webinar, you will receive a link to a short survey. If you could take a few minutes to provide feedback, please, so we can improve on future webinars, that would be much appreciated. Now, let me please welcome our speaker today. Dr. Charlotte Usher is a chartered geologist and a principal geophysicist and presented in our January talks. Charlotte is technical lead for geophysics within RSK and is actively involved in research and development, as well as working on large-scale commercial projects. She was a finalist for the Rising Star Technical Excellence category for Inspiring Women in Construction and Engineering Awards. She is looking to make the communication of geophysics more accessible to increase engagement and use in ground investigations. So I'll hand over now to Charlotte to give us an insight into choosing the right geophysics technique.
Thanks, Hugh, for that introduction. So for my talk today that I'm going to be giving and my previous talk in January have been very strongly influenced by my work on the Syria C812 guidance. So you'll probably find there's a lot of references to that within this webinar. Well, in January, I was discussing why we should be using geophysics within ground investigations. Today, I'm going to go a step further and discuss how you would go about selecting the correct geophysical technique on your site. For anybody that wasn't in my previous talk, I touched on the fact that the choice of technique is very site and technique specific. Hopefully after today you'll have a bit more of an idea why. I'm going to be discussing what are considered the most common methods that we use within near surface geophysics, and while there are others, these are the ones that were considered the most frequently applied when we were discussing this within the Syria guidance and through other literature. So that's the list I've stuck with. I'm also going to look at the best techniques to use in certain situations and also to go into things like the advantages and the limitations of those techniques. So I'm just going to quickly explain a couple of terms I'm going to be throwing around today. So firstly, we've got technique. So when I'm referring to technique, I'm talking about a specific single geophysical survey type. Whereas when I use the word method, it's a more general umbrella term for a family of techniques. Many techniques. Resolution is how detailed a survey will be, usually describing either laterally or vertically. And noise, which is any uninterpretable or unwanted component of a recorded geophysical signal. I should also mention that when I say correct technique, I'm referring to the most appropriate technique that we would advise to be used given the information that we've been provided. So firstly, I'm going to talk about how to go about selecting the correct technique. For anyone that was in my previous talk in January, you may recognize a version of this image. The first consideration we would always look at is, should geophysics even be used at all? This flowchart, of which there is a version in Syria C812, it can help you determine where geophysics may actually be unnecessary on your site. However, if your risks are high, if you aren't sure if or where there are any targets or hazards on your site, if your target is big or shallow enough and different enough in composition to the surrounding ground material, or if you'd need to drill a lot of holes to be sure of finding it or its extent, then geophysics might be able to help in this case. The choice of technique needs to be specifically tailored to your site and your target. So you need to consider things like the properties. If there's no contrast in the physical properties between your target and the surrounding material, you're not going to stand a chance of finding the buried feature. A good example of this is things like clay land drains within a clay-rich soil. They're very similar. It's going to be really difficult to see that. You need to know what your required resolution is. So how detailed do you need your results? What are the dimensions of your target and how deep do you need to investigate? These all go together in considering if the target is even detectable using geophysics. And when used alongside the consideration of the properties, you can then work out if you can potentially measure that feature. So if you've got a higher than expected property contrast, you actually have a better chance of finding that feature, even if it is buried at a considerable depth. Site conditions will caveat all of these. So if you've got a very overgrown site, which is unfortunately very common, if it's flooded, also unfortunately common at this time of year, it doesn't matter what the physical contrasts are that are present, the chosen technique might very well be unusable. And time frame, how long you're allowed to be on a site, is also another important consideration. The overall cost of a survey, as well as any specific client requirements, are obviously very important for those that are looking to commission a survey, but not always considered when looking at designing an optimum geophysical investigation. Any application of a technique, so within the survey design point, generally will be modified based on these features. The same physical properties will be measured irrespective of the nature of the target, but you have to be wary of choosing a method based purely on the cost or the ease of access, as it won't necessarily produce the best or even any usable results potentially. So each geophysical survey needs to be designed using these optimum techniques or a selection of techniques based on the target. So now I'm going to discuss the main geophysical methods. I've split these into 4 main categories. So these generally are defined by either the common properties that are being measured or similar surveying methods. First, I'm going to discuss electrical methods, which includes things like the vertical electrical sounding, electrical resistivity tomography, induced polarization, and spontaneous potential. Different ground materials will both dissipate energy, which means it allows current to pass through under a set resistance, and also to store energy, somewhat like a battery, but generally on a much, much smaller scale. The electrical properties of the ground will vary due to things like changes in the material, saturation of fluids, buried obstructions. And the techniques that I'm going to describe here are generally measure the variation in the potential voltage that is created when a current's passed through the ground, which is usually done using a set of metal stake or porous pot electrodes. And those measurements can then be converted into values such as the resistivity of the ground. This image here is one that was included in Series E812, and it shows the sort of ranges of electrical resistivities or conductivities in various geological material. Now, what I really want to highlight from this image is the possible ranges that can be measured within particular materials, particularly how these values will change based on the saturation or porosity of a material, particularly in sedimentary materials, but also to highlight the overlap between those ranges, which is really clear within particularly the sedimentary materials. Rock age also can have an influence on the conductivity. Older rocks tend to be more compressed and therefore have a higher resistivity or lower conductivity. There's several different ways that these techniques can be used effectively, including geological applications, corrosion or earthing studies, landslide assessment, mapping landfill boundaries or leachate plumes, and leakage monitoring. Firstly, the vertical electrosounding or VES surveys. These are a simple technique using just 4 electrodes, so 2 create the current and 2 measure the potential voltage. These electrodes are manually moved for each measurement. The depth and resolution are controlled by how far apart those electrodes are, and it's typically used for things like measuring corrosion of the soil or for earthing studies. It tends to produce things like a one-dimensional sounding of the resistivity change with depth at a common center point of a survey line. And it can be processed to interpret a geological model. Electrical resistivity tomography, or ERT surveys, they're a lot like VES surveys in that they use a set of 4 electrodes, but modern technology means that now many electrodes can be laid out at once, and the equipment will automatically switch between the current and potential electrodes that are required for each measurement. The depth and the resolution are again controlled by how far apart the electrodes are, but also the total line length. That in itself tends to be influenced by how much space there is available to use, and also the type of electrode array that's used. There's a lot of applications to this technique, and data tends to be presented as a 2D or a 3D cross-section of the change of resistivity with depth, which can again be interpreted for different geological materials if we have associated intrusive evidence. Induced polarization measurements, these can actually be collected alongside ERT data using the same electrodes, but instead of measuring resistivity, it's looking to measure the chargeability, so how well this ground stores energy. Chargeability can't actually be measured directly. It's estimated from a slow decrease in the velocity that's flowing through, the voltage, sorry, that's measured in the ground. The depth is again controlled by the separation of the electrodes, and the resolution by how many measurements you've recorded. Data will typically be presented on the same sort of scale as the ERT data, as either a 2D map of chargeability, for example. And why it's quite useful is while 2 materials might have the same resistivity, they may not have the same chargeability. So when using this alongside the ERT data, you can actually get additional information about the ground structure and help better define the geology. Spontaneous potential. This has been used extensively within the mining industry for things like ore detection. It measures the natural flow of electricity in the ground, so it's a passive technique. The relevant application of this within sort of the engineering environmental aspect is the assessment of water seepage from dams or embankment structures. So it's therefore used typically alongside other electrical techniques, but there's also potential applications in things like contamination monitoring. The main disadvantage of SP is the number of signals that can interfere with the measurements, so their noise basically. This can include things like changes in the topography, any sudden rainfall, changes in temperature, light intensity, any buried obstructions. So these need to be accounted for when processing. And typically the SP data will be presented as a 1D profile of the voltage measured along the survey line. That depends on the number of measurements that are being taken. Now, I'm going to discuss potential field methods. So this includes both microgravity technique as well as magnetic surveying. These are again passive techniques. They measure the variation of naturally occurring fields and theoretically have no depth limitation, but realistically they are limited as you need the signal to be measurable over other external signals such as the noise, background noise. Another issue is each of these methods are subject to something called non-uniqueness, which means that when modeling potential causes of whatever the anomaly is, there could potentially be multiple solutions possible for a single measured signal. This is another image from Sirius E812 showing the typical range of densities in various geological materials. while most geological materials tend to have a density of less than 4,000 kilograms per meter cubed, some man-made items such as steel can be between 7,000 or 8,000 kilograms per meter cubed. So this should be considered when modeling things like reinforcement. This next image shows the typical ranges of magnetic susceptibilities. So again, like the other properties I've shown, there's a lot of overlap between the materials over quite a large range of values. So this again needs to be considered. There's several different ways these techniques can be used effectively, although it will depend on the technique. Obviously, techniques here that rely on measurement of ferrous changes, so maybe things like mapping buried utilities or reinforcement, might be better when considering the magnetic technique in most cases. Although, as I mentioned before, the density of steel reinforcement is far greater than that of most geological materials, so maybe we don't completely discount gravity at this point. Magnetic surveys, they measure the changes in the magnetic field. So there is an understanding that at every point on the surface, the measured magnetic field will be a sum of the primary field that's created naturally by the Earth spinning and the secondary field that will be generated by magnetic materials that are within the Earth's crust. So that'll be any sort of ferrous minerals as well as buried artifacts. The size of any measured anomalies will be proportional to the mass of that object and will decrease with depth, basically. They're really good for rapidly mapping the surface. The kit tends to be carried by hand or towed behind a vehicle. And this will generally produce a 2D map of magnetic changes over a survey area. So we can use this to highlight any magnetic anomalies that can be targeted by second phase techniques such as geophysics or trial pitting. But this technique will be fairly useless in ground where there's a lot of metallic debris. So most signals in that case will be swamped by the noise. So this needs to be considered at the survey design stage. Microgravity surveys, these measure changes in the Earth's gravitational field. So this will be affected by changes in the density of ground material as well as the presence of buried obstructions. Data will be collected on a point-by-point basis. So this can be quite time-consuming to acquire. And it means that the technique tends to be used as a second phase technique to be the most cost-effective. It is considered one of the most effective methods of detecting voids, but the technique is quite susceptible to noise, particularly from wind or traffic, which means surveys often have to be undertaken out of hours for the measurements to be precise enough. And in certain cases, such as when there's been a large seismic event, such as the earthquake last week, surveying has to be halted and restarted again at a later time. From this, you can produce, again, a 2D map of gravity changes across the surface or a profile of measured gravity signal. Generally, we consider any low residual gravity anomalies to be synonymous to areas of reduced density, so for example, voiding. Now I'm going to discuss electromagnetic methods. So I'm going to talk about frequency and time domain electromagnetic mapping techniques, as well as ground penetrating radar surveys. So electromagnetic techniques are obviously measuring changes in the electromagnetic fields. They are sensitive to changes in both electrical and magnetic properties of the ground or target. And those are going to be influenced by things like changes in the conductivity of a material, any ferrous bodies that are present in the ground, the presence of saturation or variations in the conductivity of ground fluid, so such as you'd expect to find in contamination plumes, for example. The shallow surveying techniques are capable of really rapidly mapping an area, much like the magnetic technique, and are therefore really good to use as a reconnaissance tool, so your first phase survey. And they also require little to no contact with the ground, so they're non-intrusive and can be either hand or vehicle towed. This is another image from Sirius C812. So I've already shown the typical ranges of conductivity. This is highlighting the possible ranges of dielectric permittivities within materials. There's a real influence of how these values vary due to saturation and porosity, which you can really see within the superficial deposits. This is due to the fact that the dielectric permittivity of water is so high. So that will have a big influence on the dielectric permittivity of a material. There's, again, several different ways these techniques can be used effectively. You'll note that there's a lot of mapping or locating applications listed here, which just re-emphasizes the fact that these are used a lot as a reconnaissance tool, often to map a large area or to find and target specific features with other survey types. Firstly, frequency domain electromagnetics, these are also known as FDEM surveys. They measure changes in the electrical conductivity. So this will be through changes in both the strength and the phase of an electromagnetic field that's generated in the ground, usually from an input EM current. Again, this is commonly used as a reconnaissance tool, but it's not particularly effective when you've got a large area of low conductivity or highly resistive material. As I mentioned before, there can be a large range in the conductivity of materials, and the change of materials at really high conductivities as well can be non-linear, which needs to be considered when presenting the data. It's a really good technique to highlight buried obstructions or areas of increased conductivity, and the data tends to be presented as a 2D surface map or as a profile. Time domain electromagnetics, or TDEM. These surveys are used in a similar manner to the FDEM surveys, but they are measuring the decay of an electromagnetic field. It's particularly good at highlighting metallic objects in the ground. So there is a drone-based application for use with UXO detection. They can be used to measure geological or hydrogeological changes, so things like contamination plumes, buried waste, buried metallic obstructions, and data are again generally presented as 2D surface maps where we can highlight anomalies, as you can see in the image shown on the screen. Finally, on this section, ground penetrating radar, also known as ground probing radar or GPR. It's very well known and a very versatile piece of equipment. And like the other electromagnetic techniques, it has the potential to survey a very large area in a short period of time. And the level of detail that we can achieve with GPR means it's frequently used for the detection of buried artifacts such as services, foundations, or archaeological targets. And lower frequency GPR can also be used for mapping geological targets or hydrogeological boundaries, so your depth to bedrock or your water table. And while the range of frequencies can allow for this equipment to be used at a range of different resolutions, so with more detail, which is a higher resolution, generally this comes at the cost of depth. So the more detail you see in, the shallower you will look. Similarly, there's certain materials that don't work well with GPR, such as clay, which attenuates the GPR signal and sometimes reduces the penetration of that signal to pretty much nothing. Now, finally, on to seismic methods. So the main three I'm going to discuss are seismic refraction, reflection, and surface waves. So seismic methods, which may also be referred to as elastic or acoustic methods, they look at the variation of the elastic properties of materials. So that's how well a material recovers after it's had an external force applied and then removed, such as being hit by a hammer. Changes in that material or the saturation of that material will generally affect the elastic properties, and the seismic energy will also travel differently in the ground depending on the wave type, whether it's a body wave or a surface wave or whatever. This is an image showing the typical ranges of seismic velocities within the ground. This is mostly looking at P wave and S wave energy, which are both forms of body waves, and arrive first within a seismic signal. It again highlights the range of velocities, as well as the effect of weathering or saturation on these velocities. And again, the age of a material will have an impact, as older materials are often therefore more compressed and will therefore represent a faster overall seismic velocity. Again, there's several different ways that these techniques can be used effectively, which will generally depend on the technique being used, but this is a kind of list for the seismic techniques. So firstly, seismic refraction. This has a relatively short acquisition time compared to some of the other seismic methods, making it relatively cheaper, but the surveys are still labor intensive. It also has to assume that seismic velocities of the material only increase with depth, as it's physically impossible for energy to be refracted where there's a decrease in velocity. It is generally used to map a 2D cross-section of things like the P or S wave velocity with depth, and it can be used to help determine other seismic parameters such as the rippability of the ground or the elastic moduli, for example. Seismic surface wave techniques. These include surveys like continuous surface waves, which is CSW, multi-channel analysis of surface waves, or MASWA, and microtremor surveys. These will measure the lower frequency surface wave energy. These have longer wavelengths than the body wave energy, and that means that they can measure to greater depths. Generally, the deeper you want to measure, the longer you have to record. So for MASWA surveys, which go to typically around 30 meters, you would be measuring those for a couple of seconds for the active surveys. Whereas for microtremor surveys, measuring to a kilometer depth or more, these have to be left out for hours to days recording. As with any of the surveys, the deeper you go, generally it is at the expense of resolution. And these surveys are typically used to get geotechnical parameters such as ground stiffness or the VS30 parameter, or to help determine the elastic moduli in the ground. And the data can then be presented as 2D cross sections of these changes, or 1D soundings depending on the technique applied. And certain surveys such as MASW can be collected alongside refraction surveys using the same setup, which is really useful. Seismic reflection is a really well-researched technique. We know a lot about how to make this work from information from the oil industry. They've done a lot of the hard work. They've designed all this sophisticated software. The main problem is these software and the detailed processing steps that are required also need experience to use them. So people need to know what they're doing. But when they're used well, it can provide a lot of information in terms of the geological model. And your information tends to be presented as a 2D cross-section or as a 3D model of the ground, depending on the information they've got. And again, this needs to go alongside intrusive information to get the best, most robust model. Okay, I'm going to just kind of summarize what I've talked about here. Now I've thrown a lot of information at people. Got a nice little table, which I'm going to show now. You may recognize this from documents such as the British Standard 5930. I believe there's a version in Reynolds and in the ASTM guidelines, as well as in the new Sirius E812 guidance. And this is just looking at the usefulness of geophysical techniques under a typical site condition. So it's not true for every site. It is a generic guide, and it's a starting point to look at what may be useful in terms of geophysical methods in certain applications, but it doesn't replace advice from a geophysical specialist. And this should always be sought when designing a geophysical survey. But there are certain things like you wouldn't expect to measure the dynamic elastic moduli with any sort of method other than the seismic methods, for example. But again, it is site specific, it is target specific. The things like the magnetic surveys will only be useful detecting UXOs, for example, if those UXOs are constructed of a metallic material. So always seek advice from your geophysicist, but this is a good guide to start from. So each technique that I've discussed here is generally sensitive to changes in one or two particular properties, sometimes indiscriminately. It is important to remember that just because a target and a surrounding material may have a property in common, there may be another property that may be different enough to measure. So just because it can't be detected with one technique doesn't mean it can't be detected with another. And as always, you have to combine your intrusive evidence with your geophysical techniques for the most accurate ground model. Thank you.
Right, thank you, Charlotte, for that detailed exploration of geophysical techniques. We have a number of questions coming in through the portal. If you can keep submitting the questions, then we can quiz Charlotte now. So firstly, we live in a country that has a lot of clay soil. You touched on this in your presentation, and you're saying GPR doesn't work in clay. So what are we expected to do in that situation?
So yes, it was a bit of a broad statement that while GPR doesn't work when it's pure clay, it's more because we tend to have a proportion of clay within our soils. Its GPR is less effective when there is clay. So it depends partly on the proportion of clay within the soil as to how effective GPR is going to be. And it may be that in certain situations, yes, GPR won't work. So in those situations, we'd look at what we're trying to measure, what property contrast would be useful in that situation, and then we would potentially present the options of different geophysical techniques in the place of GPR that will potentially be as or if not more effective, hopefully. So yeah, that's what we do in those situations.
Okay, thank you. When you say multiple techniques are better, how many is multiple?
Yeah, so in this particular case, there is going to be a point where doing more techniques may become redundant. There's certainly techniques such as vertical electrical soundings and electrical resistivity tomography. We wouldn't use those on the same site because they're measuring exactly the same thing using pretty much the same method. We wouldn't bother to use those on the same site. So there has to be kind of a balance between getting different property information to help improve our geophysical model and then our geological model, but also obviously the more techniques we're trying to apply, we realize that that's going to impact the cost of the project. So it's trying to find the balance between what's going to benefit the model versus what's then going to become redundant at a certain point. So it needs careful design, and the more information we have about the target, and in certain cases there may also be it may be sensible to do trial surveys as well to then work out which of the techniques are going to work best on site to then get the best information out of that site.
Right, fantastic. So one here that I think gets asked quite a lot. Are you able to detect shallow concrete structures beneath concrete hard standing?
So in certain cases, yes. That depends, however, on if that structure is reinforced or if the, again, shallow concrete is reinforced, and also what the contrast between the top layer of concrete is compared to the bottom layer of concrete. If they're too similar, we may not be able to detect the boundary between the two, but if there is a difference in the extent of the lower layer compared to the upper layer, that might be something that would be detectable. But again, it depends on if there's reinforcement in the ground, if there's reinforcement in one of the layers and not in the other. Again, it's possible, but if the reinforcement's in the top layer and not in the bottom, again, that's going to make life a bit more difficult, because that's a lot of the techniques are going to be affected by that reinforcement. So it is possible in certain situations, but again, we could trial that sort of situation to see if it could be detectable in an area where we know it's present, to then see if it's worth then expanding geophysics to the rest of the site, because obviously we don't want to roll out a full-scale geophysical investigation and then find out that it's useless.
Yeah, absolutely. And probably related to the last question, does concrete have a noticeably higher density than natural rocks for geophysical surveying?
As I understand, this depends slightly on the construction of the material, but there can be a very close density between the two. It depends on, for example, how porous the concrete is compared to whatever bedrock it's on, or if it's on superficial deposits, then obviously that's going to be very different. So there are overlaps between concrete and natural geological materials that would have to be considered for whatever property is being measured. But again, just because it's the same in one property doesn't mean it's going to be the same in the other property. So the more information we can have on the construction of that concrete, the better.
So it very much is, once you know what you're looking for, the more information that the client can get to the geophysics team, the better chance we have of finding what they're looking for.
Exactly. We know a lot about the physics of materials. That's a well-known sort of science. It's then being able to use that in an applied way to be able to measure what we want to.
Right. Excellent. Right. I think we'll end the questions there, and further questions will be answered once Charlotte's had a chance to review these. Our next Down to Earth talk will be on Tuesday, the 14th of May, provided by our waste and permitting team. Please remember to complete the feedback following the presentation. And thank you all for attending today. We will see you again in May. Thank you very much.
Thank you.